So the next part of the titration curve we can consider is at the equivalence point. So at this point, we have equal moles of HA and OH minus. So this reaction, our HA plus OH minus going to H2O plus A minus, has gone to completion. And so what we've done is we've transformed all of our HA. So this is now gone out of solution, and we are only left with A minus. Well, besides, the counter ions that go with everything. So what we have now here is a solution of a weak base. And so if we want to find the pH of this, we do it just like we would for finding the solution of a weak base. The thing we do need to realize, though, is that the concentration has changed. So our initial concentration of our weak acid was 0.02 molar, but that is not going to be the concentration of our weak base because we've added our titrant. So the total volume of the solution has changed. So we need to take that dilution into account. So our new concentration, in the book they call this F prime, the formal concentration but now diluted, is we're going to take our initial concentration, so that's our 0.02 molar, times the dilution factor. And this will be the ratio between the volume we started with, 50 milliliters, divided by our final volume. In this case, 50 plus 10 milliliters. We know it's 10 milliliters because we calculated the equivalence point earlier. Okay, and so that's just, if you think about it, these two, if we take these two multiplied together, this will give us the moles, and then we need to divide by the new volume. Okay, so that gives us our new concentration will be less. It'll be 0.0167 molar. And then we're still going to do a weak base problem. So we need to solve Kb is equal to x squared over F prime minus x. All right, so we're going to need to find Kb, and F prime we just found. So then we're going to solve for x. So I'm going to skip those steps. Those are things that you can go back to previous chapters to double check you know how to do those things. But x is going to be 1.76 times 10 to the minus 5 molar. And remember, since this is a weak base problem now, that's equal to the concentration of hydroxide. So using the usual steps, we can change that to a pH, and that gives us a pH of 9.25. So again, I'm skipping some steps here that you should already know how to do. So again, you can either find POH and use the relationship pH plus POH equals 14, or use the KW expression. All right, and so this just goes to show that for a weak acid titration, the pH does not equal 7 at the equivalence point. Right. So this is a misconception that sometimes is present. You think, oh, I neutralized everything, so pH is 7 at the equivalence point for a weak acid. But in the case of a weak acid, what you've done is you haven't neutralized everything. You've turned your weak acid into a weak base, and so you should get a slightly basic pH whenever you're titrating a weak acid at your equivalence point. After the equivalence point, things look the same as they did for the strong acid or strong base. So if we go to, say 11 milliliters, so we're 1 milliliter past the equivalence point. Now the concentration, the pH is going to be controlled by just the excess titrant that we've added. So we have 1 milliliter excess. So our moles of hydroxide will be that 1 milliliter times our 0.1 millimoles per milliliter. So we have 0.1 millimoles. And this should look very familiar because it's exactly what we did with the strong acid, strong base titration. And then we needed to find the concentration of OH minus is that 0.1 millimoles divided by our total volume, which is now 50 plus 11 milliliters, which gives us a concentration of 1.64 times 10 to the minus 3. Now remember, that's the concentration of hydroxide. Using whatever means you want to do, you can change that to a pH. and we get 11.21. So again, a pretty drastic change in pH, which is what we need to be able to observe the equivalence point. All right, so that's the end for this video.